So in light of recent advice on campus to avoid big meetings in person, we're going to be finishing up this general chemistry class through a couple of videos to finish covering some of the concepts in chapter 13. This video will continue nicely from the other video on this channel where we were deriving rate laws. In that video we were using experimental information from experiments performed with different reactant concentrations, and we were using the rates that were measured in those experiments to determine the overall reaction order and the value of our rate constant. What we're going to look at now is a slightly different approach where we're actually going to mathematically integrate the rate law and use this as a much more straightforward way of determining the important values of constants in reactions with different orders. So we're going to focus our attention on first order reactions, and we're going to look at what the integrated law will actually tell us. So we're going to start by looking at an example, and this example is going to be a simple case where we have unimolecular decomposition. So we're taking our ozone molecule, we illuminate it with UV light, and that causes this photolysis reaction to happen where we actually break our ozone down into oxygen and an oxygen atom. If we wanted to write down the rate of this equation, what we would do is say that the rate is equal to the rate constant K multiplied by the concentration of the reactant, and we're assuming that this is a first order reaction, and so the power of our concentration factor here is equal to 1. Now previously we've written down rates of reactions with respect to how each of the reactants or products varies with time, and so we could similarly write down the rate of this particular reaction from the point of view of the change in the ozone concentration over time. Now this is a reactant, and so the reactant concentration is decreasing. A rate always has to be positive, and so we have minus the change in the ozone concentration over time. Now we've written this out using D instead of delta, and we do that because part of the process that we're going to be adopting here is actually performing an integration, and the integration of this differential function in particular. Based on comparing these two expressions, we can immediately recognize the fact that dO3 by dt must be equal to minus K lots of O3. So let's write that out explicitly. So we have dO3 by dt is equal to minus K lots of O3. So we can take a look at what this actually means in our plot of concentration versus time. So what this is giving us actually is the gradient of the slope of the concentration of ozone with respect to time. So in this plot we have concentration versus time. The value of this expression is the gradient at any point along this line. And you can see that there is clearly some curvature to this line. This axis doesn't go to 0, and so it's a little bit harder to see. But there is clearly some curvature here. It's not a straight line relationship. What we can do, though, is actually integrate this derivative, and what we'll obtain is an integrated rate law. Now we're not going to go into the calculus associated with actually doing this integration, but the result that we obtain is that the concentration of ozone at any time t divided by the ozone concentration at the very start is equal to the exponential of minus K times T. So what we have here is actually known as our integrated rate law. And this is specifically our integrated first order rate law. We can rearrange this expression to get something that has the look of a straight line to it, and that's what we have written down here. What we can do is multiply both sides by the initial ozone concentration and then take the natural logarithm of both sides. What that leads us is to the function that the log of the ozone concentration is equal to minus KT plus the log of the initial ozone concentration. This form of the equation, either form of the equation, is an integrated rate law. The reason that we've expanded it in this way is that we can see very clearly that this has the form of a straight line. If we substitute ln of O3 for y, then we have minus KT, which is minus the gradient multiplied by what will be our x value, plus some constant value. And that you can see clearly is representative of a straight line expression. And indeed, when we plot this data as the log of the concentration versus time, we get something that has this nice straight line. So this gives us a means of actually measuring a rate constant from a set of data where we're only measuring one thing changing over time. Okay, so let's look at a quick example of how we can actually use the integrated rate law. And the way that we use the integrated rate law is, one, we have to be able to identify whether the data that we have is consistent with a first order rate law. And secondly, we can use our integrated rate law to actually determine the value of the rate constant. So we're going to do that for this reaction here, where we're taking N2O5 and it's decomposing to NO2 and oxygen. So the first thing we want to do is actually test whether or not this decomposition reaction is indeed first order in N2O5, and then if it is first order, we want to determine the value of the rate constant. So we can write out what the integrated first order rate law would look like for this reaction. So we're taking the natural logarithm of the concentration of N2O5, and that must be equal to the log of the initial concentration minus KT. This is from the form of the integrated rate law that we derived, or that we showed on the previous page. So if indeed this reaction is behaving as a first order reaction, when we plot ln of N2O5 against time, we would expect to see a straight line. So we would get a straight line. So this is one of the main tests that we can actually do to ensure that our experiment is actually a first order reaction. The experiment itself would involve measuring the concentration of N2O5 as a function of time, and then we have to plot this data in such a way that we can test whether it is a straight line in this format. So the procedure that we have to adopt would be, firstly, to take the natural log. It doesn't have to be the natural log, it could be any log. Take log of each concentration, and then we plot it as a function of time. We can see, plotting the logarithm of N2O5 versus time, we get this nice straight line. So this is our confirmation that this is indeed a first order process. The next step is to actually determine the value of our rate constant. The value of our rate constant is minus the value of this slope. So the slope of this line is minus k, and the slope of this line we find is minus 0.00693, and the units are just per second. So to determine a slope, we're taking the change in y divided by the change in x. So that gives us these units of per second, and when we rearrange this, we can identify that our first order rate constant is 0.00693 per second. So this process is a general test of first order kinetics. If the data that we collected gives us a straight line when we plot it in this form, then it's a very strong indicator that we are indeed dealing with first order kinetics. And it also gives us a methodology for easily determining the rate constant for that first order process. We can go one step further using our integrated rate law, and we can actually determine the half-lives of our reactants in a reaction. When we look at a rate constant, it gives us an indication of how fast the reaction is going, but it's not particularly conceptual. It would be very difficult to immediately look at the value of this rate constant, for example, and give any estimate on the sorts of time scale that might be involved in the actual reaction. When we determine a half-life, what we're actually calculating is the time it takes for the concentration of the reactant to decrease by a factor of 2. So that is the definition of the half-life. So if the reaction rate is faster, we're going to reach that half concentration sooner, and so we'll get a smaller half-life. For our first order process, we can write out our integrated rate law. We're going to write it out just for a general reactant x, and we're going to write it in the form of x over x naught is equal to the exponential of minus kt. When we're interested in the half-life, we're interested in this ratio, x over x naught, being equal to 1.5, being equal to 0.5, 1 over 2. So we can set this equal to 1 over 2. And when we set it equal to 1 over 2, we have to define our t as being t1/2. So we'll add that into the next line in our calculation just to make sure we're aware of this. What we're trying to do is actually solve for that t1/2 value. So we can take the natural logarithm of both sides. That gives us minus k t1/2 is equal to the logarithm of 1 over 2. And then we can rearrange this to get an expression for our half-life. t1/2 is equal to minus the log of 1/2 divided by the rate constant. And this was true for any first order rate process. What we will typically find is that actually this logarithm value is actually enumerated, and when we enumerate it, we find that the half-life is just 0.693 divided by k. So we see this very clear inverse relationship between our rate constant and our half-life. So this is the first order, this is for a first order reaction. We've shown that we can use the integrated rate law to actually determine a value of k, and from that we can determine the half-life, which is a more conceptual value for how fast the reaction is going. We know that after one half-life, for example, the concentration of the reactant is going to have decreased by a factor of 2. So in this particular example, you can see plotted here, we're starting with N2O on the left-hand side, and that's decomposing to form N2 and O2. At the start, we have 16 molecules. After one half-life, we'll be down to 8 molecules. After another half-life, we'll be down to 4 molecules. And you can see that every time a half-life occurs, we're going to be decreasing the concentration of our reactant by a factor of 2. When we want to expand the complexity a little bit more and look at second-order reactions, what we find is that our integrated rate law looks somewhat different. So we're going to start with the more simple case where we have a second order reaction, but we'd have just one single reactant. So we're looking at this example of NO2 decomposing to form NO and oxygen. If we were to assume that this was a first order process and we were to plot the logarithm of NO2 versus time, what we'd see is that there's actually some curvature. So this is testing first order kinetics. And the fact that it's curved means that this is not a first order process. So this is curved, so therefore it's not first order. In fact, this is a second order process, and the second order integrated rate law looks like this. So this is somewhat arbitrary looking, but it's derived in the exact same way as the first order rate law by an integration step that again we're not going to cover in this video. But what our second order integrated rate law tells us is that 1 over the reaction concentration is equal to Kt plus 1 over the initial concentration. So this, again, when we compare it to a straight line, we can say that 1 over x is equal to y. We have some constant multiplied by x plus a constant. And so we can identify that if we were to plot 1 over x versus t, we would have a gradient equal to k and an intercept equal to 1 over x naught. And that's exactly what we're looking at in this plot here. We have this nice straight line, and we can determine the reaction rate and also the initial concentration very easily. We can also derive half-lives for a second order process, and we do this in the same way, although it's a little bit more involved just because the mathematics are a little bit more tricky. But our half-life for the second order reaction is given by this expression. T half is equal to 1 over k multiplied by the initial concentration. So what we have to note here is that for our second order reaction, the half-life is actually dependent on the starting concentration. So it depends on the initial concentration. Whereas for our first order reaction, T1 half only depended on the rate constant. So let's look at an example where we're going to calculate the half-life for a second order reaction. The second order reaction that we're interested in is the decomposition of NO2. And we're told that K is 0.544 per mole per second, so these units are consistent with a second order process. And we're told that this is occurring at some temperature, and the initial concentration of our NO2 is 0.01 molar. So we're looking to find where our concentration is actually dropped to 0.005 molar. We've just shown our expression for the half-life for our second order process. which was that T1/2 is equal to 1 over K multiplied by the initial concentration. So in this case, we're dealing with NO2. And we have all the information given to us here in the question. So we have 1 divided by K, which is 0.544 per mole per second, multiplied by 0.01 molar. We cancel out our molar units here. We can get rid of our moles, and we have 1 over per second. So as expected, the units here that we obtain are going to be in seconds. We plug those numbers into our calculator. We find that the half-life of this process is 184 seconds. So what we've looked at in this portion with the second order reactions have been unimolecular decomposition. So we started with just one reactant and it's decomposed to form some products, and it's very easy to explore that from a second order reaction perspective because we're dealing just with the one reactant. When we have multiple reactants present, what we actually find is that the process becomes a little bit more involved. We have more things that we have to think about changing over time. So what we do actually is try to simplify that down, and one way of doing that is to introduce this idea of pseudo first order reactions. So when we're dealing with a reaction that has two reactants and it's overall a second order reaction, what we have is that a rate expression looks like this, where we have the rate constant multiplied by the reaction, the concentration of reactant X multiplied by the concentration of reactant Y. When we simplify this process and generate a pseudo first order reaction, what that means is that we're actually increasing the concentration of one of the reactants such that it's essentially unchanged during the reaction itself. So we're taking our second order process here and we're saying that the concentration of X is high enough such that over the course of the reaction, as we're reacting all of Y, the concentration of X essentially remains constant. So this gives us a pseudo first order reaction. And it's a pseudo first order reaction because we can write it in this form, where we've actually bundled the concentration of X in with our rate constant. So we can actually define our K prime here as being equal to the original rate constant multiplied by the concentration of X, where X is significantly greater than the concentration of Y. So we're essentially assuming that X remains constant. We can then tackle this procedure, or we can tackle this kind of reaction as if it were a first order reaction. So it simplifies the analysis quite considerably. The final kind of reaction that we're going to look at is a zeroth order reaction. And a zeroth order reaction is pretty rare. What we'll more commonly find is a reaction where certain reactants are zeroth order. So for example, in this reaction between NO2 and carbon monoxide to generate NO and CO2, when we write out the rate equation, we find that it's overall second order, but it's second order in NO2 and zeroth order in carbon dioxide. So what that means is that if we vary the concentration of carbon dioxide, carbon monoxide, vary CO concentration, then we don't vary the rate. So it's very rare to have any kind of reaction that's overall zero order, but it's much more common to have certain reactants present that are zeroth order. If we were dealing with a reaction that was zeroth order overall, then we could derive an integrated rate law, and the integrated rate law would look like this. So we'd have the the concentration of X would be equal to the initial concentration minus KT. So it would just decrease linearly over time, and we could plot X versus time, and then the slope of that relationship would give us minus K. So as something of a summary for all of the rate laws that we've looked at and the integrated rate laws that we've looked at, we can construct something of a flowchart. And this is when we're dealing with a single reactant. So when we follow through this flowchart, we can actually identify which order of kinetics we're dealing with, and then we can see what information is going to be pertinent. So the first thing we should do is plot the concentration of our reactant versus time, and if it's linear, then that tells us we have something which is zeroth order, and then the slope of our plot of concentration versus time will give us the rate constant. If when we plot concentration versus time we don't see a linear relationship, then the next step is to test for our first order kinetics. So we're testing first order kinetics. If our logarithm of the concentration versus time is linear, then we have first order kinetics, and the slope of that line is equal to minus our rate constant. Finally, if when we plot our logarithm versus time we don't see a linear relationship, then we can try for second order kinetics. And when we test for second order kinetics, we're plotting 1 over the concentration versus time, and if that is linear, then we get a slope which is equal to K, and it's a straight line. So one can follow this flowchart and identify firstly what order of reaction that we're dealing with based on the data that we're given, and from that information we can just straight up use the integrated rate law expressions or the half-life expressions in order to determine certain values from our reaction.